0 degrees Celsius. What is the specific heat of the metal? Well, for this we know that the heat that the metal lost is equal to the heat that the water gained, because the temperature of the metal went down, the temperature of the water went up, and the final temperature, which stayed constant, would be the temperature of both the metal and the water. So first we need to write everything in for the metal. The metal has a mass of 25.06 grams. And we're trying to find the specific heat of the metal, so that's our unknown, that's our C. The change in temperature of the metal, if you say 100 minus 32, you end up with 68 degrees Celsius. So that is a change in temperature of the metal. Is equal to, now all of this that we just did was for the metal. It's an important point to note that when we look at this, so everything that we did right here, this is all for the metal. Now we want to do the same thing, but write everything for water. So let's start with the mass of water. The mass of the water is 76.95 grams. And multiply that by the specific heat of water, which is 4.184, and that's joules over gram degrees Celsius. And then multiply that by the change in temperature of the water. Notice the water did not change temperature very much. That's because water has a very high specific heat. It takes a lot of energy to change the temperature of water. So we subtract 32 from 29.5 and we get 2.5 degrees Celsius. So now we solve for C. Now notice that everything that we just wrote down for was all of this information was for, all of this was for water. That was all for water. Now we want to solve for C, and specific heat of water is going to be equal to all of the things about water multiplied together, then divided by the 68 and divided by the 25.6. And when you do that, you should get a value of the specific heat of the metal being C is equal to 0.472, and the units for that would be joules over gram degrees Celsius. And this is a number we'd expect because specific heats for metals are typically less than 1 because they do not, it doesn't take a lot of energy to raise the temperature of a metal. It gets hot very quickly. This is our last problem for today. In this one, we're actually, instead of putting a metal in water, we're pouring two samples of water together, one warm, one cool, and seeing what the final temperature would be. So this is our final example. This is number 3. For this one, the Q that the warm water lost is equal to the energy that the cool water gained. So the energy went from the warm water into the cool water. So let's first write the values for the warm water. So we'll say 50 grams, because that's a mass of the water. It says 50 gram sample of water at 100 degrees Celsius is poured into a 50 gram sample of water at 25 degrees Celsius. What is the final temperature? We know the specific heat of water is 4.184, and that's joules over gram degrees Celsius. And the temperature of water, the change in temperature of the water, for that we're going to say 100 minus T final. Because we know the T final is going to be somewhat less than 100. And then we do that, this is all for the warm water, we set that equal to the cool water. The cool water is going to be 50 as well, times 4.184, and then times the change in temperature as well. Now for this change in temperature, I'd like to keep both of these values positive. So for this one, I know the final temperature of the water, of the cool water, is going to be higher than its initial temperature, so I'm going to say T final minus 25. Now what I have to do is distribute these values. So I say 50 times 4.184 times 100, and for that I get the number 20920, and the units for that are just joules because that's the only thing that's left. And then I actually take that and multiply the 50 times a 4.184 times a TF, and I get this value. I get minus 209. And the units for that are joules over degrees Celsius TF. Then I do the same thing on the other side. And when I do that, I multiply the 50 times a 4.184 times a TF, and I get 209 again, but this time it's positive, so I get 209 joules TF, that's a 209 for TF for final, degrees Celsius. And then I multiply the 50 times the 4.184 times the 25, and this time I get minus 5,230. Running out of room a little bit there. So on the right-hand side we have 209 joules TF over degrees Celsius minus 5,230, and the units for that would be joules. Now I want to combine similar terms. So what I do is I take the negative 5,230 over to the other side and combine it with the 20,920. When I do that, I get 26,150, and that's joules. And on the other side, I move the 209 over and add 209 and 209 together. 209 becomes positive, and I get positive 418. And the 418 is joules TF over degrees Celsius. And this one was just joules. So I want to get the TF by itself, so I'm going to divide both sides by 418 joules degrees Celsius. And divide this side by the same thing, 418 joules degrees Celsius. When I do that, what happens is the joules cancel out on both sides. The degrees Celsius cancels out here. The 418s cancel out. And I'm left with TF is equal to 26,150 divided by 418. And it's going to be, the units will be degrees Celsius. And the T final ends up equaling 62.6 degrees Celsius. So that's my final temperature. Thanks. That's the last problem.